Welcome back to ECE 501 or 441A, 541A. Lab number 1 is due Monday, the 3rd. A week after that is homework number 3. That's due. It's now posted. The problem statements are yet to be on there for you. And just to keep your calendars clear, the second exam is the 21st of October. And if you haven't done so already, it probably would have helped if you would have watched lecture 3.1 before today's class. But you can probably learn something by going back and watching that or looking at the notes, because what it is it's a different state space representation. It's an input feed forward state space representation for the same transfer function that we will look at today, but today we'll do it differently, and we'll do it with what's called phase variables, meaning we'll get two different state space representations for the same transfer function. And I've been trying to remind you that state space representations are not unique, and that's why I've been saying a state space representation for a given problem or transfer function. Then we will look at transforming from the state space representation, which is the time domain, into a transfer function, and what should you be thinking when you see that goal? Cheer 1. Yes. So this is cheer number 1, actually. So we know how to do that. We know how to take a state space representation and go back into a transfer function, but I just want to make sure that everybody's clear with how we can chase our tail. And then we'll start looking at a state transition matrix. We'll introduce and discuss that. Let's then start today with another state space representation, and the idea here is that we're factoring the transfer function, and that's going to allow us to create a different block diagram structure for the transfer function, and that different structure will then produce a different state space representation. Let's begin with the same transfer function that we were using Monday, or in the previous lecture, which was, I think, recorded on Saturday. I can't keep my days straight. This seems like Thursday, but it's Wednesday, right? Is it Friday? All right. Please show up then on Sunday if this is Friday, and we'll have a service or something. We'll do, I'm sorry, a lecture we'll have then. But it's Wednesday, I believe. Here's b sub 2 s squared plus b1s plus b sub 0 all over s cubed plus a sub 2 s squared plus a1s plus a sub 0. As a reminder, that's the output transfer function over the input transfer function as far as signals. Can you tell me anything about the denominator polynomial? It's third order. Anything else? Have we had another way of describing such a polynomial? The transfer function is strictly proper, meaning the numerator power is strictly less than the denominator power. But we've actually normalized the denominator, so this is a monic polynomial in the denominator. There's a 1 sitting out here, and if there wasn't a 1, we would factor out that leading coefficient and push it upstairs. We would divide all of our numerator coefficients by that constant, and that would produce this monic transfer function. What we want to do is factor this y over u into two pieces. It's not going to take much to mess me up or confuse me today, so that's fine. You'll have fun, maybe. And I'm doing this trying to be colorful by design. I've now split the transfer function, or the representation or the ratio of y over u, into two pieces and introduced an artificial or an arbitrary variable w. But I now have y over w times w over u, which in the black transfer function or ratio, you could think of that u is still the input, but what's w in that case? If I could cover up with my hand that blue piece of that equation, what would w represent? That would be an output, right? And then in the other one, w is the input to the output, and the overall input and output are u and y. Meaning, if we now want to write this consistent with how I factored this, what I'm suggesting is the blue piece is really the numerator. That's b sub 2 s squared plus b1s plus b sub 0. And this is the y of s over w of s times, and now we don't have anything other than a constant, and that constant is 1 in the numerator after we've pulled out the numerator. And downstairs we have the s cubed plus a sub 2 s squared a1s plus a sub 0. And this piece is our w over u piece. And what we want to do is start with that rightmost transfer function that has a constant 1 as its numerator and find a block diagram for it to begin with. So let's work on finding a block diagram representation for the first half, or the right piece of this expression. 1 over s cubed plus a sub 2 s squared plus a1s plus a sub 0. And what I want to do now is cross multiply, make it just one equation, and inverse Laplace transform at the same time. Meaning, and put all the terms except the leading or the highest power derivative on the right. Leave the highest power derivative on the left, put everything else on the right. I'm going to do that in one step. That's what that implied arrow means. What's the highest power derivative? It's going to be third. It's the third derivative, and of what variable? And there's only two, so you could flip a coin. 1. Okay, it's not going to take much to confuse me, but 1 is not going to confuse me. We have w and u. W is one possibility, and u, with the letter u, not y-o-u, is the other possibility. W is going to be differentiated, and that's the only thing that's being differentiated when we take this into the time domain. U is just going to be u of t. And we have the third derivative of w, and then we're putting everything else on the right side, meaning we now have an a sub 2, w differentiated twice, minus an a sub 1, w differentiated once, minus an a sub 0, w, plus u. And now that should just be screaming at you to put into a block diagram or into an analog computer, where we can start building that analog computer with w triple prime, or the third derivative of w, actually being the output of a summing junction. and the right-hand side, all of those pieces will come in as inputs to that same summing junction. And if we do that, let me start here with my summing junction. And I now said the output of that is going to be the third derivative of t. And if I go all the way to the right, I know one of the inputs to that summing junction is u of t. Now, how do I bring in the others? I'm going to need a w differentiated twice, a w differentiated once, and a w by itself. And how do I generate those from what I've sketched so far? Just keep integrating. If I integrate w triple prime, I end up with w double prime. I don't need to multiply A2 yet. What I'm trying to do, those A's or coefficients are going to weight these signals when I come back and feed them into the summing junction as inputs. But yes, I need to keep track of those coefficients. Right now I'm just trying to have fun with my integrators. And this will now be W prime. Oh boy. You guys are going to be upset at me, but I'll do it in a minute. Did you guys bring your scissors and tape for your notes? I can virtually do this, but you guys there are no tomatoes, right? Yes, we have green tomatoes. Those aren't going to be coming my way, are they? And this is now W of t. But now that we have all of our W's and those differentiated, we can start introducing. I shouldn't even give you guys any ideas, should I? Relative to food. There's now part of the right-hand side. We already had another part, which was u. We can find a minus a1. That's scaling w prime. And we then have a minus a sub 0 scaling w. Meaning this piece of our block diagram will actually allow us to generate this artificially created signal w of t from our original system. And this actually gives us the dynamic behavior because it gives us the denominator. The roots of that denominator give us our dynamics of the system, which if you factored it, you would find out how this system is behaving, whether it's stable, whether it's oscillating, etc. But this is not all of the system because that's just the right side of it. We need to now incorporate the blue piece, which is now going to be a relationship between the output y and this newly introduced variable w. Let me go into the blue color scheme. I now have y over w is the original numerator. B sub 2 S2 plus B1 S plus B sub 0. And if I cross multiply, maybe I'll do this in more than one step, but this is now B sub 2 S squared. This is the easier one to do. That's why I'm doing it, I guess, instead of the last one, which was more difficult, but that was earlier in the morning when we're fresher. So now, now we need to take this into the time domain. And that should be trivial. We have y, and then what's the first term on the right? It's the second derivative of w scaled by b sub 2, and then we have our other derivatives of w. And again, what we want to do is view this as the output of a summing junction. And because we already have introduced one summing junction, this summing junction is going to go over here on the right. So I'm going to call that the output of the right summing junction. And this is the inputs to that same summing junction, which is over on the right. And now you know, oh, did you run out of room on the right of the paper? I have an infinite width too, I guess, but here's where you're going to really start complaining. And the reason I now have to do that is I needed to squeeze it so you could see it before. I guess I should have had you do some origami and fold your paper so that you could then unfold it and now put in these top lines. But do you see now what we want to do? We want to generate our output y of t, which is a linear combination of these variables that we just created, w, w prime, and w double prime. If we start with w, we need to scale that with b sub 0, and we have one of the inputs to that rightmost summing junction. Then we come back over here to w prime, and that gets scaled by b1, and then b sub 2 is scaling the second derivative of w, and that now produces all three terms, input terms, to that rightmost summing junction, which is y of t, and voila, we now have a block diagram, an all-integrator block diagram that will solve that transfer function's system of differential equations associated with that system between the input u and the output y. And that should just, I don't know, just should make you feel comfortable. It should slow your heartbeat down. This block diagram just should be very comforting. All integrator block diagram. You don't know about that? Well, it will become very comforting. Because now, if you now have this, is it essentially quite straightforward to find a state space representation? That's what we want to do with this. Now that we've built it, they will come, and who's coming is a state space representation. Somewhere I've heard that if you build it, they will come. Well, we're building it. We built this block diagram, and now what is available to us is our state space representation. And what's the strategy for producing a state space representation from an all-integrator block diagram? How do we do that? So now we simply label the outputs of our integrators as state variables. And I'm going to label this one as x sub 1. And this is x sub 2. And this is x sub 3. And now do you see how I could change that up? I could relabel that, and your state space would still be describing the same system, but your representation would be different from mine if you juggled those labels on the outputs of those integrators. But I'm working from the output side to the left to produce a more standard representation, which is the phase variable form. So that now I could erase all of those w's and I have x's to work with. The strategy was that these states in your state space representation are outputs of the integrators. And if we're looking for a state space representation, I now need to find first order equations describing x1 prime, x2 prime, and x3 prime. Where in this block diagram is x sub 2 prime? I'm sorry, x sub 1 prime. It's just x2. It's the signal coming in to that rightmost integrator. That's x1 prime, but that's also just equal to x sub 2, and there's our very first equation. X1 prime is equal to x sub 2. And we could write that out in this way if we wanted to, and I could ask you to fill in the blanks. Maybe that's what I'll do on the exam, is just make it fill in the blank. Be a lot less time consuming to grade. And then you might have more than just yes and no answers. Maybe I'll make some of it multiple choice. I'm toying with you now. But now what do? I fill in these blanks. And that now populates the top row of my A matrix and the top row of my input matrix B. Wasn't x1 prime supposed to just equal x sub 2? And that's what this is saying. x1 prime is equal to x sub 2. What is x sub 2 prime? Well, we want it, again, to be this linear combination of states and input. From this block diagram, what's the first derivative of x sub 2? That's just x3. And now we can come down here and we can say, oh, this is 0, 0, 1, 0. And now we have the second row of our A matrix and B matrix filled out. And x sub 3 prime is where we get a little bit more interesting description, because now that's x3 prime is actually this double triple prime that we had identified before, and now it's this linear combination of all of our states and the input. So if we work from x1 to the right, we have minus a sub 0 minus a1. Maybe I shouldn't have had that plus sign in there. That's maybe confusing, but you could do something like this to keep track of those. And this is now minus a sub 2. And now the input comes through with just a gain of 1, because that was our numerator when we factored out that numerator. And what is the output y? We want it to be a linear combination of the states and input. And we can figure out what it looks like in terms of weightings on our state variables simply by inspecting this all-integrator block diagram. We have b sub 0 scaling x1. We have b1 scaling x sub 2. We have b sub 2 scaling x sub 3, and we have nothing scaling u. And we're now in a position with these 4 lines to create our ABCs. and D, which is in this case 0, since that's what this guy is. Meaning we now can write down x prime of t is equal to a x of t plus b u of t. Y of t is equal to cx of t plus du of t. Populating those matrices, A has a nice structure. What's the top row in A? It picked off x2, didn't it? The second row picked off x sub 3, and the last row is where we had our most business going on, and that was these negative coefficients, a sub 0, a1, a sub 2. What's B look like? Did I make it the right size? Is it supposed to be tall and narrow? Because we had one input, we had three output, or three state variables for that input matrix. It had nothing going on in the top two rows and a 1 in the bottom row. What about, so that's our system matrix A, our input matrix B, our output matrix C, and our direct feed-through matrix D. What does C look like? Those are our B's. We have B0, B1, B sub 2, and we have 0 for D. And what I want you to be able to do, now that we've gone through that derivation, you should be able to, if somebody gives you a transfer function g of s, and they say, give me a state space representation, do you see how you could now just say, oh, I'll give you a phase variable representation and write down A, B, C, and D directly without rederiving anything? You know exactly where those coefficients reside in the A, the B, the C, and the D. So if I give you a transfer function, you should be able to, we did it this morning. We said, oh, here's our G of S. We went to a block diagram, an all-integrator block diagram, or in the earlier times, an analog computer. We could actually do that in the lab. You could hook up those integrators with gains, summing junctions, and solve differential equations. Did you guys do that in your differential equation class, or did you play with pickaxes? The latter of the two? So if you weren't digging in the soil in your differential equation class, you could have been doing analog computer solution with this. And today what we did is we went here, and then we went into a state space representation. From our block diagram. Is this the only way to do that? Anyone want to answer that question? Who watched Monday's lecture? So that shows another way of doing this, which is the input feed forward approach. So there are many ways to navigate from G of S to the state space, but what I was suggesting just now is if I give you a G of S, you could go directly there, right? Now that you've done this once, and we've done it a second time on Monday, in Monday's class. But how do you get in this direction? How do you get from state space to G of S? Tier 1. So this is now G of S is equal to C Si minus A inverse B plus D. So if you start with the state space, Cheer 1 gives you the transfer function. And if I gave you a state space, do you see that you could produce a block diagram? If I gave you this or this, do you see how you could connect that up into an all-integrator block diagram? You could now go to here, and then what could you do with this? Mason's gain. You could play with paths and loops and have a lot of fun. And then you could get your G of S. So now you know how to go back and forth in this diagram. Now what we want to do is relate these concepts even more in terms of going between time and frequency domain representations. Or time and frequency domain representations can be related for linear time invariant, which we sometimes abbreviate as LTI. If you're texting, you can just say LTI. LTI systems. Because I know you need to get this information out. Maybe you're using Twitter. I heard a big report on Twitter. Who's going to try to buy that one out now? Disney's thinking about it, so they're going to put the happy face on Twitter, I guess. I don't. Current event, contemporary issue. Maybe there'll be a quiz on that, or that'll be a question on the exam, maybe. Let's now look at how we can relate these two. So let's consider a scalar time invariant system. And if I say scalar, what does that mean? That's a constant, and so that's the size of our A matrix. This system matrix is 1 by 1. Or we're now looking at our A, B, and C being constants. And so I'm labeling those with just lowercase a, b, and c so that our state space representation looks like x prime is equal to a x of t plus b u of t, and y of t is equal to c x of t. And what we want to do now is find the solution of that first order differential equation. And we can do that by Laplace transforming. And because we now want the solution, we want to keep track of our initial conditions. We don't just want the transfer function now, we want a solution. And the solution can involve what we're driving our system with, the input, and initial conditions. That can produce our system response. What happens when we Laplace transform a derivative? S, we now have an S, capital X of S. Anything else? Do you remember anything else accompanying that? And then we have an initial condition, and that was minus X of 0 minus. That's time t equals 0 minus. That's on the leftmost side of the origin, or time t equals 0. That's all that means. What happens when we Laplace transform a x of t? What's a? We said it was a constant, so that just flows right out or factors out of our Laplace transform operation. And we simply have a times x of s. And if we do the same thing or think the same with our input, we have b u of s. Again, a and b are constant. And we want to now find little x of t in the time domain. So it'd be nice if we could find an expression for capital X of s and then inverse Laplace transform. Let's combine our terms that involve capital X of s. S minus a times capital X of s is equal to x of 0 minus plus b u of s. I can solve this for capital X of s. That's now 1 over s minus a times the initial condition plus, let's say, b over s minus a u of s. And I may actually want to put that b with the u in a little bit, so I may just pull it outside that square bracket just for fun. Actually, it will make more sense in a minute. Now, what is the inverse Laplace transform of 1 over s minus a? Was that on your crib sheet or the piece of paper that you forgot to copy for the exam? Did you need it? Maybe not for exam 1, but you can bring it next time. Table, what, 2.3? Something like that. What's the inverse Laplace transform of this? So, because I'm putting my minus sign there, this is actually e. All I have to do is mention Disney, and here comes Mickey Mouse, right? So the inverse Laplace transform of 1 over s minus a is e to the at. Does anybody even care what we're doing now? But we give this expression, I know if you're hungry that looks like eat, but it's e to the exponent at. Somebody's hungry, aren't they? But you'll never forget that, hopefully. You can say, oh, I'm hungry. That's the state transition matrix. If you're going to transition between any points, you need some food. You need to eat. So here's your state transition matrix, e to the at. This is now the state transition matrix, where the system matrix, in this case, what is our system matrix? That's typically given by capital A. What is that in this case? In this example? A is A. But typically we refer to our system matrix as a capital A, but in this case we're working with a scalar system and it's just the lowercase a. It's just this 1-by-1 matrix, little a. And that's in the exponent e. And that's now going to allow us, since this is a constant, we now know how to take that first term into the time domain. That's just e to the at times the initial condition. And that's our initial condition piece of the total response for x of t. But what does this look like over here? We want the second piece That's a product in the time or in the frequency domain. What's the product in the frequency domain do in the time domain? Convolution. So if we called this h of s and this g of s, we could think of recalling facts that h of s, g of s in the frequency domain is, in the time domain, this convolution integral from 0 to t, h of t minus tau, g of tau, d tau. And if we now want to inverse Laplace transform, which is what we're suggesting, 1 over s minus a times b u of s, we called this h of s and this g of s. What's that look like? Did we find the inverse Laplace transform of 1 over s minus a? That's this e to the at. Bless you. So now we need to do the convolution from 0 to t of h of t minus tau, which is e to the a t minus tau, b u of tau, d tau. This is your favorite convolution integral, loosely speaking, your favorite. And now we have the two pieces to find our total solution. X of t is now equal to the term due to our initial condition, so there's the initial condition response, plus a term due to the driving function or the input, e to the a t minus tau, b u of tau, d tau. Meaning, if somebody now gives you a scalar differential equation that's linear and time invariant, this will be the solution. You have to know the a, you know the input b, or the weighting on the input, which is b, and now you can solve that. You have this convolution integral on the right, and if you don't have any input, all you have is this initial condition response, which is impacted by the state transition matrix, which is e to the at. And that state transition matrix helps influence how the input comes in to drive the state, because it's now inside the integral with this e to the a t minus tau. Now what? Well, we can't just keep crawling, right? We've seen the scalar case. What we want to do now is we want to grow up and attack the vector case. We want to be big boys and do the vector case. Again, we're going to be in the time invariant, and we now have x prime is equal to ax plus bu, y is equal to cx, and in this case, a, b, and c are constant. I'm going to give you the punchline, and then we'll come back and tell the joke on Friday. How's that? So the punchline is as follows. Now x is a vector, and you're now going to have e to the at, and that's a as a matrix. It's now a 3 by 3, a 10 by 10. On the exam, maybe a 6 by 6. And now you need to matrix exponential that. plus the integral from 0 to t of e to the a t minus tau b u of tau d tau. Doesn't that look very similar to what we just did, except now we've replaced lowercase with uppercase? We just put the cap lock key on and we typed the same equation. Except when we had the t's, then we went back and shifted down and did the t's and the taus. And hopefully you have some Greek letters on your keyboard to do the taus. But this now has the state transition matrix, a matrix exponential. It has this piece, which is the initial condition response, and it has this piece, which is our forced response. And we want to be comfortable playing with those in the vector case of our state or with the scalar case, but they structurally look very, very similar. And as I said, here's the punchline, and we'll tell the joke on Friday.